There are 7 ways a star can die, and the last one is so violent it leaves nothing behind. Not a corpse, not light, not even the atoms it was made of. Everyone, bluntly, in 10 minutes. But first, what actually kills a star? Simple. Every star is a constant tug-of-war between two brutal forces. Gravity wants to crush it into a single point. Fusion in the core pushes back hard with radiation. As long as it has fuel, it burns hydrogen into helium, then helium into carbon, balancing gravity's grip. When the fuel runs out, the outward push stops. Gravity wins, always. Every time, no exceptions ever. Here's the thing. How spectacularly gravity wins depends on exactly one specific number: mass. Nothing else really matters. Not composition, not age, not location, not luck. Mass. A star's birth weight is a sealed death sentence. Light stars die quietly. Middle stars die dramatically. Heavy stars die in ways that rewrite whole galactic regions. And the heaviest stars die in ways physicists still bluntly argue about at conferences right now today. So we're going to walk through 7 deaths, from the lightest, most boring corpse in the cosmos up to the kind of blast that could easily sterilize entire planets thousands of light years away. Ready? Good. Let's start with the most boring corpse in the entire cosmos. First up, red dwarfs, the runts. These are the true runts of the stellar universe, anything under about 4/10 of a solar mass. They're small, dim, and cool. They also happen to be the most common type of star in our galaxy. Roughly 3 out of 4 stars you can't even see with your eyes are actually red dwarfs. Here's what makes them weird. Red dwarfs are fully convective, meaning the whole star churns like boiling plasma soup. Fresh hydrogen keeps mixing into the core. They burn cold, they burn slow, and they last a very long time. We're talking trillions of years. The universe itself is only about 14 billion years old, barely a blink. Pay attention here. Not a single red dwarf has ever died. Ever. In the entire history of the cosmos. Theoretically, when a red dwarf finally runs dry, it doesn't explode, doesn't shed its layers, it just fades out. It shrinks into a blue dwarf, then eventually a black dwarf, a cold, dead cinder radiating basically nothing. No supernova, no fireworks, no funeral. Just a slow dimming into the dark. It's the least dramatic ending imaginable. We've never actually seen one, because the universe is too young. Bump the mass up and things get interesting. Second death. Sun-like stars. Anything from about 4/10 of a solar mass up to roughly 8 solar masses. Includes our Sun, obviously, and it dies in a way that's both beautiful and pretty rude to nearby planets. Here's how it goes. The star burns hydrogen for about 10 billion years. Fine, boring. Then the core runs dry. The core starts fusing helium. When that happens, the outer layers puff up massively into a red giant. The star swells hundreds of times its original size. If you're a planet orbiting close in, you get swallowed. For our Sun, that means Mercury, Venus, and probably Earth. Cooked, engulfed, gone. In about 5 billion years. After a while, even helium runs out. The core can't fuse carbon, not enough gravity to squeeze. So the star's outer layers get gently blown off into space, forming what's called a planetary nebula. Gorgeous glowing rings of gas. Nothing to do with planets, by the way, just a historical naming accident. What's left behind is the actual core, naked, exposed, and roughly the size of planet Earth itself. But it holds half the star's original mass, packed into a ball you could fit inside a country. This is a white dwarf, made mostly of carbon and oxygen, crystallized under absolutely insane gravitational pressure. Basically, a diamond the size of a planet, glowing faintly from leftover heat, cooling for trillions of years. That's our Sun's ultimate fate, a cosmic diamond drifting through the dark. Now cross the mass threshold. Third death, core collapse supernova. This is what happens when a star is born with more than 8 solar masses. And this is where the universe stops being polite. A massive star burns through fuel absurdly fast. It's not measured in billions of years anymore, it's measured in millions, sometimes just a few million. Hydrogen, helium, carbon, neon, oxygen, silicon. The core fuses heavier elements, each stage shorter than the last. Silicon burning at the end lasts maybe a day, one single day. And then the core hits iron. Here's why iron matters. Iron is the exact element where fusion basically stops paying rent for the star. Fusing anything into iron releases energy. Fusing iron into anything heavier costs energy instead of releasing it. So when a star's core finally turns to iron, the fire simply goes out. Instantly, all at once. Outward pressure vanishes. Gravity, waiting patiently this entire time, takes over completely in less than a single second. The core, roughly the size of Earth, collapses to the size of a city in less than a heartbeat. Protons and electrons get crushed together into neutrons. The infalling outer layers slam into that rigid core and bounce. That rebound is the supernova. For weeks, one dying star outshines its entire host galaxy, every star combined. It hurls its outer layers into space at a fraction of light speed, leaving behind a lone neutron star. A ball 20 kilometers across, so dense that a single sugar cube would weigh 1 billion tons on Earth. A teaspoon of neutron star matter weighs more than Mount Everest. Push the mass higher and neutrons break. Fourth death, direct collapse to a black hole. This one is genuinely unsettling, and here's where it gets weird. Born with more than 25 solar masses, sometimes the core collapse supernova simply stalls out and never fully ignites. The outer layers, instead of flying across the galaxy, fall back into the collapsing core. Everything just keeps falling. The neutron star stage gets skipped entirely. Nothing in the universe can push back against that much gravity. Matter crashes itself past where known physics applies. Space-time falls shut, a singularity forms, a black hole silently born. Here's where it gets weird. From the outside, the star just vanishes. No explosion, no flash, no planetary nebula. One night it's there, some nights later it isn't. Astronomers call this a failed supernova, for years purely theoretical. Then in 2015 they caught one, star N6946bH1, 25 solar masses, sitting in a galaxy about 22 million light-years away. It brightened briefly, then it disappeared. No supernova, just gone, replaced by a black hole that swallowed itself into existence. A star tens of times the sun's mass. Poof! But there are weirder deaths, ones that need a partner. Fifth death, Type 1a supernova. It requires a companion. And it produces the most consistently violent, most useful death in astrophysics. Picture a white dwarf orbiting another star. That Earth-sized diamond corpse we mentioned earlier. The white dwarf's gravity is intense, pulling material off its partner. Hydrogen, helium, whatever's available. That stolen matter piles up on the white dwarf's surface. It gets heavier and heavier. There's a hard limit, the Chandrasekhar limit, roughly 1.4 solar masses. Hits that number, something breaks. Electron degeneracy pressure gives out, temperature spikes, carbon fusion ignites, not gently, but everywhere in the star at once. The result is a thermonuclear runaway. The entire white dwarf detonates, flash burning into oblivion in a matter of seconds. Nothing survives. No neutron star, no black hole, no remnant, just an expanding cloud of nickel and iron debris. Here's why astronomers love them. Type 1a supernovae always detonate at the same mass, releasing the same energy, which means they always shine with almost exactly the same brightness. So astronomers call them cosmic standard candles. Compare how bright one looks from Earth to how bright it should be up close, and you get distance. This is literally how we measured the expansion of the universe. This is how we discovered dark energy. Type 1a supernovae are basically the rulers we use to map the cosmos. Now scale up to impossible stars. Sixth death. Per instability supernova. only hits monsters between 130 and 250 solar masses. Stars this big are rare today because the physics of star formation makes them ridiculously hard to build.
But in the early universe, with nothing but hydrogen and helium around,
these giants were far more common. Here's what happens. Inside a star this massive, the core temperature gets ridiculous, and fusion gamma rays start misbehaving. They spontaneously convert into particle pairs, electron and positron, antimatter twin. Pure energy becoming matter, exactly as Einstein predicted. The problem is, those gamma rays held the star up. When they turn into particles, that pressure suddenly drops. The star starts to collapse, but that triggers a runaway fusion event in the core. It basically eats itself. It explodes outwards so hard, nothing's left behind. No black hole, no neutron star, no remnant. Total annihilation. These are the brightest stellar explosions ever recorded, visible clean across the observable universe, billions of light-years away. In 2007, astronomers spotted SN 2006 GY, the top suspect for pair instability. It shone brighter than 100 typical supernovae for months. And one more class makes even this look small. Seventh death, hypernova and gamma-ray burst, the extreme end. Stars over 250 solar masses spinning fast. When their cores collapse, they don't just make a supernova, they make a hypernova plus a gamma-ray burst. Here's how it works. The core collapses straight into a black hole. Infalling matter forms a spinning accretion disk. Magnetic fields wind up the spin axis, and two particle jets fire from the poles at near light speed. These jets punch through the star's outer layers and blast straight out into deep space at relativistic speed. For 10 seconds, that burst outputs more energy than our Sun produces in its entire 10 billion year lifetime. 10 seconds versus more than 10 billion years, all focused into a single narrow beam. Basically insane. Here's why you care. Gamma-ray bursts sterilize. A hit from within a few thousand light-years, aimed at Earth, our ozone layer gets stripped. Cosmic radiation fries the surface. Mass extinction. Basically, the sky kills everything living. Some scientists think a nearby gamma-ray burst triggered the Ordovician extinction 445 million years ago. Here's where it gets uncomfortable. There's a star called WR104, a Wolf-Rayet giant 8,000 light-years away. It's a candidate hypernova progenitor, and its rotation axis appears pointed roughly in our direction. Uncomfortable. If it goes off, and it will, and the beam is aimed right, we get essentially no warning. The gamma rays arrive at the same instant as the light announcing the explosion. Zero reaction time. Probably we're fine. The alignment might be off by a few degrees, enough to miss us entirely. Probably. That's the point of this list. Somewhere in the universe, right now, every one of these deaths is happening. Red dwarfs burning, sun-like stars shedding layers into gorgeous nebulae, massive stars collapsing into neutron stars and black holes. White dwarfs are being stolen from. And somewhere, right now, a hypernova is firing a gamma-ray burst across space. What does all this dying build? Here's the payoff. Every atom heavier than iron was forged in stellar death. Gold, silver, uranium, iodine, zinc, the calcium in your bones. Supernovae, neutron star collisions, dying giants made them. The rare, precious, biologically essential elements only exist because stars died and scattered their guts across the galaxy. The iron in your blood is supernova shrapnel. The gold in a wedding ring is neutron star debris. You are quite literally made of star death. Every one of us. The universe recycles corpses into everything next. That's the whole thing. 7 ways to die, from a red dwarf's slow fade to a hypernova's beam. Same tug-of-war between gravity and fusion, 7 different endings, one universe built out of all the debris. Subscribe for weekly uploads. I bluntly explain one big thing every single week. No fluff, no filler. Want to know how black holes actually work? Event horizons, warped time,